Today you're going to watch part 1 of the video, Life Cycle with Stars. And we're going to start today with a brain pop.
Dear Tim and Moby, how do stars burn out? From Corey. This is one of my favorite topics. Stars change throughout their lives just like we do, only they live for billions of years instead of a few decades. They start out as clouds of gas and dust called stellar nurseries. The force of gravity slowly pulls particles inside these clouds closer together, causing dense clumps to form. If a clump grows large enough, the pressure caused by gravity inside one of these baby protostars begins to generate heat. This heat and pressure build until nuclear fusion reactions begin to take place in the core. Gravity pulls hydrogen atoms together, smashing and fusing them into heavier helium atoms. Nuclear fusion generates an enormous amount of energy, causing the star to ignite. This is the beginning of the longest part of the star's lifetime, or its main sequence. That's where our star, the Sun, is right now. It's about 4.6 billion years old, which means it's a little less than halfway through its 10 billion year long main sequence. Well, what happens to a star after its main sequence depends on its mass. Astronomers actually don't know what happens to low-mass stars, those with less than about half the mass of our Sun. They may actually have a main sequence that lasts more than 1 trillion years. That's longer than the current age of the universe. Midsize stars, like our Sun, become white dwarfs. Those are super dense objects, about as massive as the Sun, but only a fraction as big. They're around the size of the Earth, actually. A couple of things will happen before the Sun turns into a white dwarf, though. The Sun will begin to die when it uses up all the hydrogen in its core. At that point, the Sun will expand, ballooning to many times its current size. Stars in this stage of their life are called red giants because their surfaces cool down to a red glow. Plus, they're really, really big. The Sun will start burning helium at that stage, fusing it into even heavier elements. Eventually, it may get so big that it engulfs the Earth. Oh, don't worry, we'll all be long gone before that happens. It's billions of years away. Anyway, after no more than about 1 billion years as a huge red giant, the Sun will begin to collapse under the pressure of gravity. It'll actually get kind of unstable, expanding and contracting and shedding its outer layers in the process. The remains of those outer layers form a big cloud of gas and dust called a planetary nebula. Nope, they don't have anything to do with planets. They're just called that. But you know, you've probably seen some awesome pictures of planetary nebulas from the Hubble Space Telescope. These are pictures of stars that are at the end stages of their lives. It's kind of like watching what will happen to our Sun way before it actually does. Anyway, at the center of a planetary nebula is a core of carbon, which, after cooling, finally becomes a white dwarf. Well, that's the route our Sun will take, but it's not the only way a star can die. Stars much bigger than our Sun collapse so quickly that they explode into a supernova, scattering stellar material far and wide. A supernova explosion can last for a month or longer, and during that time it can be as bright as a galaxy with 1 billion stars. The clouds of gas and dust that supernovas spew out are where heavy elements are made, and they lead to the formation of new stars. The core that's left over can go one of 2 ways, depending on the mass of the original star. If the star's about 10 times as massive as our Sun, the protons and electrons in the core are crushed into neutrons. What you get is a neutron star. Some neutron stars spin rapidly, emitting pulses of radio waves. These are known as pulsars. If, on the other hand, the original star was more than 10 times as massive as the Sun, its supernova core will collapse in on itself. It will keep collapsing until it forms a tiny area of infinite density called a singularity. We call this a black hole, and its gravity is so powerful that nothing within range can escape it. not even light. And nothing you throw into a black hole will ever come back. We actually have a whole other movie on those, so you should go check it out. Well, time to take the trash out. You know, we could just take the trash out to the corner.
So hopefully that brain pop was a really good overview for you of all of the different possible paths that a star can take in its life. There are a few important things for you to understand when we're talking about stars and their lives. Stars can exist for billions of years. The length of their life depends on when they run out of fuel for fusion, which is hydrogen and helium, to go through nuclear fusion. One way that we can take a look at where stars are at in their life cycle is by looking at something called the HR diagram. HR stands for Hertzsprung and Russell, which are the two scientists that came up with it. And this diagram shows the relationship between temperature and magnitude. It also shows how stars evolve and change over time. Here is one variation of the HR diagram. This is a nice visual one. And you can see that on the y-axis we have luminosity, which is brightness or magnitude. And the units here are solar units. So if a star is a 1 on here, that means it's the exact same brightness as the sun. And so we follow this over, you can see the sun is right there. So all of the stars up here in the upper half are brighter than our sun, and all of the ones down below it are dimmer than our sun. And then at the bottom you can see we have surface temperature, and also we have color down here. And remember, that's because temperature and color are related, right? So the hotter ones are going to be blue and the cooler ones are going to be red. And I want you to notice a few things with this diagram. You can see that most of the stars are along this kind of section in the middle here that's labeled main sequence. Some of the ones above it are giants and supergiants, and then below here we have white dwarfs. You're going to be exploring a lot more with the HR diagram. So the first stage for all stars is formation. This is when gravity pulls together gas and dust in a nebula to form a protostar. So let's take a quick look at an animation of this. So here's a nice visual of how a star evolves. Stars are born deep in the center of dusty gas clouds in interstellar space. So here's an example of a nebula that they're zooming in on. And then the cloud begins to collapse under gravity. And as more mass builds up in the center, it becomes hot and the cloud starts to spin faster and faster. The spinning causes the cloud to flatten. And here we see some of the other matter in the disk as it starts to accrete and stick together. And then as more matter accretes, they start to become planetary bodies. And so this shows the formation of our solar system. You can see the inner planets there and some outer planets, with the sun at the center. The second stage for all stars is the main sequence. And remember, in the HR diagram, that's where we saw most of the stars existing at. During this stage, energy is generated in the core by nuclear fusion. This is the longest stage of the life cycle, and stars spend most of their lives in this stage. During this stage, the size stays the same. After this stage, when the star has used up all of its fuel and run out of fuel, it becomes either a giant or a supergiant. During this stage, its outer atmosphere is expanding and cooling off. And the center actually shrinks, and it's the atmosphere that's expanding. The way we classify between a giant and a supergiant is if a star is up to 10 times bigger than our sun, we call it a red giant. And if it's 100 times bigger, it's a red supergiant. So our sun is going to become a giant, not a supergiant. It's not massive enough. Here's an example of Aldebaran next to our sun. This is a red giant. It's about 44 times the diameter of our sun. And here is Canis Majoris, which is a red supergiant. And so you can see how much larger this is. So down here, a little dot down there would be the size of our sun. So you can see it's almost 2,000 times the size of our sun. So the final stage for giants is going to become a white or black dwarf. A white dwarf is a small, hot star, and it's just the leftover center of an old star. So what happens in that red giant is that outer atmosphere is expanding, and it just continues to expand, and all of that mass just kind of goes out into space, and then you're left with the leftover center. There's no fuel left, so fusion is not happening. But they can still continue to shine for billions of years. Once they stop shining, then they're called a black dwarf. Here is Sirius B, which is the white dwarf companion of Sirius A. And together they make the brightest star in our night sky. Now let's take a look at what happens during the evolution of a low-mass star. So here's an example of what will happen to our sun as it evolves. And our sun is a very typical low-mass star. And here you can see the orbits of Earth and Jupiter. And as hydrogen fuel is used up in the core, gravity then begins to squeeze, causing the core temperature to rise and pressure to increase. 200 million years from now, it will be too hot for people to live on Earth. And then as it enters the red giant stage, it's going to start to expand. So in 500 million years, the oceans and atmosphere will boil away due to the increased temperature and pressure of the sun. At this time, hydrogen fusion will be in a shell around the growing core of solid helium. And our sun will be slowly moving off of the main sequence into the realm of the red giants. About 2 billion years from now, the sun will be larger than Jupiter's orbit, and helium fusion will start in the core. And the sun will be a red giant. And this is the beginning of the death of the sun. Over the course of another billion years, the core will build up solid carbon with shells of hydrogen and helium fusion above it. 500 million years later, the crush of gravity will try to ignite carbon fusion, but it will fail because there's not enough mass. The outer layers of the sun will blow away, revealing the sun's hot core, which is a white dwarf. We're going to pause here for today for part 1, and you will watch part 2 later, and then we'll talk about the evolution of higher mass stars and what happens to those supergiants at the ends of their lives.